talked a lot about the observatories down in Chile over the past couple of years. He's given presentations here, and he's a member now of AAI, so I'd like to turn this over to you, Bill.
Thank you, Mary. Well, I see a number of friendly faces here. That's always encouraging. So if you attended Dr. Charles Liu's talk in the September meeting at the Smith Auditorium, you will have already heard about the topic, which is the Legacy Survey of Space and Time. What is it? Well, it's a 10-year survey, and I'll go into more details about that later. What I liked about Dr. Liu's presentation was the tremendous enthusiasm he showed for this remarkable project and for astronomy in general. But I at least have some different slides to show you and some new information. And I hope you'll leave with your sense of wonder enhanced that human beings can attempt to understand billions of objects in the universe by creating instruments that take trillions of measurements of these objects and use these measurements to develop a deeper knowledge of the universe than mankind has ever had before. So tonight you'll learn about the 5 surveys that are part of the Legacy Survey of Space and Time. You'll learn about the 4 science goals that the survey supports. The work takes place, to begin with, at Vera C. Rubin Observatory in Chile. Inside the observatory is the magnificent new telescope, the Simonyi Survey Telescope, and built into that is the LSST camera. The camera we'll go into some detail about as well. The real difficult part of this survey is the data processing afterwards, and I think you'll understand why that is as we go along. Now, given all that data, there are 8 science collaborations that take advantage of the data. We'll mention each of these briefly. And then what about you? What about me? What can we do with this avalanche of data that's going to be coming our way? Citizen science topic explores that. And finally, there are a couple of online tools we'll go over that you can use to play around with the universe. So what is this Legacy Survey of Space and Time? The survey actually consists of 5 surveys. There's the Wide, Fast, Deep survey, which is the bulk of the observations, and 4 more targeted surveys. The survey takes place over 10 years, and it's primarily of the southern sky. Each area of the sky is photographed twice every 3 or 4 nights. So this is how Rubin is going to show us how changes occur in the night sky over a huge portion of the sky. How much data is involved? 20 trillion bytes of data every night. If you were to take each byte of data and view it as a centimeter thick, a tiny bit, and stack those bytes end to end, beginning at the sun, the stack would reach almost to the orbit of Mars. So it's just an unbelievable amount of data. And in all, it's going to be 500 petabytes, 500 quadrillion bytes of data. And I don't want to think about how far that would go. The final data set is going to include billions of objects and trillions of measurements of those objects. And in addition to that, a time-lapse movie of the entire southern sky is going to, in effect, be created. So I want to tell you some more about the parts of the sky and the frequency of imaging in those parts. The color-coded map shows the parts of the sky included in each of the 5 surveys. Some of the sky is never visible from Rubin's 30 degrees south latitude, namely the part above 60 degrees north. And so the images of that region can never be made from Rubin Observatory. Another part of the sky is always visible from Rubin. That's the part 60 degrees south and further south in celestial latitude. The remaining parts are sometimes visible and sometimes not over the course of a year. Some very visible and some hardly visible, but at least visible. But there's another issue here, which is the quality of the images you can make. Because when you get within about 30 degrees of the horizon, that there's a tremendous amount of air that you have to go through in order to image anything, to see anything in the sky. And for that reason, turbulence in the air degrades the images, and so they're not as useful for scientific purposes. So 30 degrees is sort of a limit that's, for the most part, hewed to in this case. Now, for example, the part of the northern sky that's 30 degrees north is going to be visible, but it won't fall within that. It won't be above 30 degrees at any time. So, for the most part, you don't want to observe those parts of the sky. On the other hand, there are areas of the sky that are of great importance. The part that's not just going to be imaged at all is in gray. Okay, so what are the surveys? We have the wide, fast, deep survey. That's from 5 degrees north celestial latitude to 65 degrees south. That's the green band for the most part. And that is the main focus of the legacy survey. Now, the interesting thing there is shown in that color diagram at the very bottom. It goes from purple to yellow with green toward the right side. The wide fast, deep survey requires each area of the sky to be imaged about 825 times over 10 years, as is shown by the green color of the map and on that legend at the bottom. But there are other surveys as well. For example, the North Ecliptic Spur Survey. That extends into the northern sky because the ecliptic, the path that planets and asteroids, comets stay relatively near, goes up into the northern sky. That's how we can see Mars and Jupiter and so on up high in our sky at times, or the moon for that matter. Anyway, we do want some pictures of that, but not as many. About several hundred images of areas can be obtained as indicated by their purple color on the map. Another area for some of the survey is the South Celestial Pole Survey. That one obtains several hundred images of areas that are above 30 degrees elevation only half of the year. Then there's the Galactic Plane Survey, and that one is of interest because the Milky Way, our home galaxy, extends not just, well, the best views are in the south, or in the southern hemisphere, like between Scorpio and Sagittarius among the constellations, but there are northern hemisphere constellations that have the Milky Way as well, like Cygnus, for example, the Swan. And we need to see some of those areas because star formation happens there and exoplanets may be discovered. And those are some of the areas the survey is concerned with. And then finally, the deep drilling fields. Those are image are indicated in yellow here because they're going to get uh, up to 1,200 images taken per year, and those are just a few special areas. The yellow spots on the map indicate those. Okay, so what science is going to be done with all of this? Well, the Legacy Survey of Space and Time has 4 science goals. The first of these is probing dark matter and dark energy. Astronomers do this by measuring type 1a supernovae, by exploiting gravitational lensing by huge clusters of galaxies, and then by detecting large-scale structure in the universe. So that's probing dark matter and dark energy. And that's important because gathering information about large-scale structures that billions of galaxies have formed over cosmic time will help scientists model the evolution of the universe and test various theories about the nature of dark matter and dark energy. The second science goal is to create an inventory of the solar system. For example, how many asteroids are there? How big are they? What are their orbits? And the same for comets. And what we ask is also, do any of those bodies endanger life on Earth? You've probably heard of near-Earth asteroids and how people are quite concerned that one of them might impact the Earth as one did 65 million years ago, leading to the dinosaurs' extinction. It could happen again. Well, hopefully we won't find one that we have to destroy or be destroyed by. Maybe we'll find a new planet. So the LSST will help with that effort also. Now, about 1 million asteroids and comets are known so far. The LSST is going to reveal millions more. Having a complete census of near-Earth objects is essential for defending our planet against potential asteroid impacts. During the initial tests of the Simonyi telescope and the LSST camera, 2,104 new asteroids were discovered in about a week, including 7 near-Earth objects, none of which fortunately pose a hazard at this time. So the video I'm about to show you shows both actual images from the survey of newly discovered asteroids and then a representation of these discoveries night by night. And these representations are color coded. So I'll say more about that in a moment. But here's the video. And you can see the kinds of images that are produced. These are from the commissioning work done to test the system back in the spring. Now what you see here are dots that are color-coded. Cyan for main belt asteroids, blue for Trojan asteroids in Jupiter's orbit, purple for trans-Newtonian objects, and yellow for near-Earth asteroids. So that's, you notice Vera C. Rubin Observatory has a long name. The National Science Foundation and the Department of Energy want to make sure they get some credit for this marvelous installation. So going on, there are 4 science goals. We've talked about probing dark matter and taking an inventory. The third science goal is mapping the Milky Way. The LSST is going to yield a 3D map of about 20 billion stars in our home galaxy, which has 100 to 400 billion stars. Structures left over from past mergers involving our galaxy will be revealed, evidence how the Milky Way was formed. Now, the LSST's 3D map of the Milky Way will cover almost 100 times the volume of previous surveys. And the color and brightness of the stars in the Milky Way will also be cataloged. And finally, a better knowledge of our home galaxy will help astronomers understand galaxies in general. The fourth science goal is exploring the transient optical sky. This includes objects that move, such as asteroids, comets, and interstellar objects that streak through the solar system. It also includes objects that change in brightness, such as variable stars, exploding stars, stars that suck material from other stars, and perhaps changes in brilliant active galactic nuclei. For example, only 3 visiting objects from outside the solar system have ever been detected. The latest of these is 3I Atlas, which Alan Witskell mentioned in his public night talk a couple of weeks ago. 3I Atlas is expected to emerge from the sun's glare in early December, and the LSST is expected to reveal many more such objects over the next 10 years. Well, the legacy survey of space and time will be conducted at the Vera C. Rubin Observatory. The Rubin Observatory is located on Cerro Pachon in Chile's Atacama Desert. The observatory is 8,769 feet above sea level. Its funders are principally American, namely the National Science Foundation and the Department of Energy. Its operators are the NSF's Noir Lab and the SLAC National Accelerator Laboratory. That used to be the Stanford Linear Accelerator Laboratory. I should mention that the observatory is named for the American astronomer Vera C. Rubin, who studied galactic rotation rates. It turns out the galaxy rotates much more like a rigid body than you would think. In our solar system, for example, distant planets move much more slowly around the sun than the Earth does. Ones closer in move faster. And that sort of relationship you would expect to hold in the galaxy, but it doesn't. It doesn't really look like a spinning LP, but the outer regions go faster than you would think. And these measurements that she made about rotation rates led to the hypothesis that there is something called dark matter that doesn't interact with ordinary matter except gravitationally. Here's a picture of Ms. Rubin. It's a photograph from 1963. She was using the Kitt Peak National Observatory's 36-inch telescope and attached spectrograph. Now let's talk about the great telescope inside Rubin Observatory, the Simonyi Survey Telescope. The Simonyi uses a 3-mirror design, and there's a short video that depicts the light path through the telescope, and I think this is set up so that I'm going to have to narrate. So if you hear music, something wrong or right perhaps happened. So you can see inside this telescope, it's got a primary and tertiary mirror together, made from one piece of glass, and its whole diameter is 8.4 meters. The ring is the primary mirror. Light comes down, is reflected to the secondary, back down to the tertiary, and up to the camera, which has 3 lenses in it. I might mention, let's see, well, I forget what I was going to say. Never mind. So let's talk in more detail about the Simonyi telescope. It's got several notable features. First, it uses that 3-mirror anastigmatic design. That means that it corrects for spherical aberration, coma, and astigmatism. You can ask questions about that later, but basically the scope in the dome there, the big scope, corrects for spherical aberration and coma, but not astigmatism because it has only 2 mirrors. Rubin has 3. Another factor about this is that it has fast f1 optics. You know, the fastest SLR lenses have about what, f1.4, f1 maybe, f1.2 I think is one that Nikon has. But these 3 mirrors are all very highly curved and have what's called fast optics. And that yields this huge 3.5 degree field of view. That's 7 full moons across. But having this 3 mirror design yields a highly curved focal surface. So how do you get a highly curved image to lie flat on a CCD detector array? We'll talk about that with the camera. Now, the Rubin telescope has an alt-azimuth mount. Our telescopes here have equatorial mounts, which means they can rotate about one axis when they follow the stars moving across the sky. But Rubin and all the other great telescopes, like at the Mauna Kea and in Paranal and the new one on Armasones, have these alt-azimuth mounts, which give much sturdier support for massive telescopes. But the axes are vertical and horizontal. The vertical axis gives you rotation like left to right, and horizontal up and down. But that's like your body, you know. If you think about it, you want to watch something in the sky, you have to sort of pivot around on your feet and raise your head up as things go up in the sky. So you're a walking alt-azimuth mount, whether you knew it or not. So what's that involve? For one thing, in the case of Rubin, rapid target acquisition. Rubin is able to go from one part of the sky to an adjacent part of the sky, accelerating, decelerating, and damping vibrations in 4 seconds. I'll show you a video of how it moves, and it'll be hard to imagine it stopping and settling in 4 seconds. So rapid target acquisition, but as I mentioned, because it's an alt-azimuth mount, the field of view rotates as it tracks objects in the sky. And that would lead to smudging images if you didn't do something about it. And that's handled in the camera. So let's see. I was going to give you an example. If you think about watching Orion rise in the east, Orion appears to be lying on his right side. But by the time he's high in the sky, his head is pointed up. And so you can imagine on your retinas, his image is lying on the side on your retina. But by the time you see him high in the sky, his image is right side up. And if you were trying to do a long time exposure, you can imagine the blur you would get as that image shifted on your retinas. Well, the same thing would happen in this camera if on Rubin if we didn't do something about it. A couple more things about the technology. It has active optics, which means these big mirrors are somewhat flexible. And so as they rotate during observation, they tend to warp out of shape. And that has to be fixed, obviously, or you would completely mess up your images. It's done by actuators behind the mirror, and they operate at about like 10 times a second based on some calculations that a computer system does. There's also, and that's to maintain mirror shape. There's also something in astronomy that I've talked about here before, which is adaptive optics. Essentially, it's the untwinkling of starlight so that fuzzy images become crystal clear, like Hubble images, where, you know, Hubble and James Webb, for that matter, don't have to deal with the atmosphere. since they're in space. But our atmosphere is a churning soup of air molecules, and light goes through it and gets distorted, and that's a big problem. But with adaptive optics, that distortion can be alleviated in small areas at one time. But Rubin's got an enormous area to deal with, and so adaptive optics is not practical. Rubin is much more at the mercy of atmospheric conditions than the great telescopes on Mauna Kea or Paranal and other parts of the world. Okay, so I think, oh, I should point out that the early financing was thanks to Charles Simonyi, a software billionaire. Here's a picture of the Simonyi Survey Telescope. You can see the M1, M3 integrated primary tertiary mirror at the bottom. The secondary mirror is a convex mirror at the top. And then the camera comes down through a hole in the secondary mirror, and the lenses there are at the very bottom of that black cylinder there in the picture. Another image of the Simonyi is from the top. I wanted to show you this because you can see the edge of the M1 mirror, the primary mirror, and the edge of M3, the tertiary mirror integrated at its center. The blue part up there is the utility trunk of the camera. Okay, now here is a short old movie that shows the Simonyi in motion. That's tons and tons of material.
Is that actual speed?
Huh?
Is that the actual speed?
Yeah. So it can move quickly. I think the web people are getting a kind of a jerky image compared to what you're seeing here. It's going to be coming back, but it does settle quickly. I don't know who put the tape there in the way, but that's the way it is. So I think you get a good sense for how quickly that can move. By the way, the primary mirror, tertiary integrated mirror has not been installed. Only the commissioning camera was present in that video. Now we need to talk about the camera, which is a really spectacular piece of engineering. As I mentioned, it has 3 lenses, and their purpose is to flatten the focal surface. They don't introduce chromatic aberration into the system because of the way they're figured. So the point is to flatten the focal surface, not to distort the colors. This camera has 6 filters, and at any one time, only 5 are mounted, so you have to choose one. And they range from the ultraviolet U band to visible lights G and R bands to infrareds I, Z, and Y bands. So pictures are taken in monochrome with the Rubin, and any colors that you see are introduced later in post-processing. The detector is an amazing thing. It's got 3,216 megapixels. Your phone cameras have, what, 12 or 24 maybe megapixels? So this is just an enormous scale difference. And those pixels each cover about 2/10 of an arc second in the sky. Also, the detector itself is contained in a cryogenic environment, and so it operates at 150 degrees Fahrenheit below zero. And the camera itself, which you'll see in a moment, is mounted in another device called the camera rotator that takes care of compensating for field rotation due to that alt-azimuth mount. And the camera was built by the Department of Energy's SLAC National Accelerator Laboratory. Fortunately, all this was completed before the massive budget cuts in recent months. So there's the camera. Does anybody have a single lens reflex camera handy to compare with? Well, you can see the two guys bowing in worship of that device there for scale. So here's an exploded view of the camera. The L1 and L2 lenses are mounted together at the front of the camera. 5 filters occupy a carousel that can rotate one of them into the light path. And in back of the carousel is the third lens, L3. And then behind that is the detector array. And I want to go into some detail about that. The detector array is composed of a bunch of 4K by 4K sensors, charge coupled device detectors. And they're grouped into 2 different kinds of groups. There are 21 science raft towers with 9 CCDs each. And then there are 4 corner raft towers with 3 CCDs each. And you'll see how those fit together in the next slide. I should point out again that the cryostat that contains the detector array operates at 150 degrees below 0 Fahrenheit. And that's because much of the work of this scope is done in infrared. Well, infrared is heat, right? And so you must make sure that the device itself doesn't introduce any heat into the recording. So here is, let's see, can someone mute, please, online? Okay, so this is an image of the detector. Each CCD contains 16 megapixels, that's 4K times 4K, and each raft of 9 CCDs thus contains 144 megapixels. Remember, there are 21 of those rafts. And then finally, the 4 corner rafts have 3 CCDs for a total of 48 megapixels. So it's 4 times 48 plus 29 times 144 for the total number of megapixels, which is 3,216. To get an idea of how big the thing is, check this out. You can see the image of the full moon is just a tiny fragment of that mock-up of the detector. 47 of those images could fit on that detector. And in case you're wondering, that's Suzanne. Seems like she should get some credit, right? Okay, well, let's see how the Simonyi telescope and the LSST camera compare to some other large telescopes in their images. Those telescopes are the Vista Survey Telescope and the Very Large Telescope's unit telescopes, there are 4 of them, on Cerro Paranal. And then the extremely large telescope is being built on Cerro Armazones. You can see that the Simonyi is slightly bigger than the VLT unit telescopes, but much smaller than the ELT. The Simonyi's field of view, though, is twice as large as Vista's and far larger than the VLT and ELT scopes. The resolution of the telescope and imager combination is certainly best for the ELT. That's a 0.004, 4 thousandths of an arcsecond per pixel. But the Simonyi and LST cameras resolution is between those of the Vista Survey Telescope and the Very Large Telescope scopes, really, on Paranal. And let's see, the imager, I've showed you how many pixels the LSST camera has on the Simonyi. The ELT is in second place with 150 megapixels. Well, clear winner there. But the real heart of the survey is going to be the data processing. There's an enormous flood of data that's coming from the legacy survey of space and time. I mentioned 20 terabytes of data per night. They're going to be transmitted alerts for every event that's detected, every change in brightness or motion that's detected, and they'll be distributed within 60 seconds. So a notable event would be a change in either brightness or position that is not random. So there's a 5 sigma significance limit imposed on these changes. So they have to be pretty sure that it's not just some random occurrence in the weather or something else. And interestingly enough, you or I or anyone in the world can subscribe to alert brokers or data brokers to get these alerts. Of course, you don't want all 10 million of them. Probably you'd want to subscribe to something that looks like a comet, for example. Now, the LSST is going to deliver its main data sets, all the data, not just the changes, in 80 hours from the time of collection. It has to be processed in California. And those data sets are going to include processed images and also catalogs of objects updated with the latest information. And once a year, the survey will release a reprocessed data set, which will provide images that are deep stacks. The more images you can put together, the more noise reduction you can do on those images. Now here is an interesting map. It shows how fiber optic cables link the observatory at Cerro Pachon down to Santiago, Chile, and then up to Florida, perhaps going through Brazil. And once in Florida, it goes across country to the SLAC headquarters in Palo Alto and down to the headquarters of Noir Lab. And also from SLAC, it goes to a French data facility and from there up to a UK data facility. So people are quite serious about making this data available to many parts of the world. And that's 20 terabytes of data per night. Now, the key to making sense of this deluge of data is to have computational algorithms that can process the data efficiently, and they're smart enough to detect rare events. Well, who gets to use the data? That's governed by the LSST's data access policy. There are two classifications of LSST data products, public and proprietary. Public data products are shareable with anyone, anywhere. And they include the alert packets and the prompt products database. The proprietary data products are accessible only by Rubin data rights holders. They include promptly processed images, not the alerts, but the images, and the annual data releases. But the proprietary period only lasts for 2 years. Once that period is over, then all that data becomes public. Well, who can be a data rights holder? First, US scientists, second, Chilean scientists, and then international members who join through either the Noir Lab or the SLAC, National Accelerator Lab. Now, what's done with the data? I mentioned that there are 8 science collaborations. I want to go through each of them to give you an idea of the breadth of the projects that are going to be impacted by this tremendous new facility. The first is galaxies collaboration. These astronomers will study the formation and evolution of galaxies over cosmic time. The second collaboration is stars, Milky Way, and local volume. The local volume is the part of the universe within 32 million light years of our Milky Way galaxy. Well, these astronomers are going to study the accretion history and structure of the Milky Way and the local volume. They'll also investigate fundamental properties of stars within 1,000 light years of the sun. The third collaboration is solar system. New methods are needed for analyzing data on over 5 million asteroids and Kuiper belt objects. Those are beyond the orbit of Neptune. But also survey strategies are important. Optimal survey strategies for efficient use of the telescope. And those will have to be developed for the solar system in particular, because that's where you have so many changes occurring with the asteroids being detected and comets. The fourth collaboration is dark energy. Methods are needed there for obtaining state-of-the-art, robust constraints on the cosmology, the study of the universe as a whole. So there are 4 more collaborations. Number 5, active galactic nuclei. These are tremendously energetic parts of remote galaxies. They typically have a supermassive black hole in the middle and an accretion disk of a huge amount of material and great jets of charged particles moving at near light speed coming out from the area in the black hole in each direction. Collaboration number 6 is transients in variable stars. The astronomers in this group study supernovae, exploding stars, pulsating variable stars, because they're of interest, and sometimes they explode, and then transiting exoplanets. That's how one of the methods of discovering remote planets in our galaxy is by their dimming of light when they pass in front of their star. And this system will be able to detect that sort of thing. Number 7 is strong lensing. That's gravitational lensing of distant objects by massive closer objects like clusters of galaxies. And the idea there is you can get the total mass distribution of galaxies and groups of galaxies and clusters of groups by doing this study. Also, this group will be interested in testing predictions of the cold dark matter model of cosmology, which is right now the ruling model of how the universe developed. And it can be tested on a subgalaxy scale. And finally, informatics and statistics. You can imagine with 20 terabytes of data coming at you, you better have good methods for analyzing massive amounts. And that's what these folks will be working on. Scientists will be dealing with the Rubin Science Platform in doing their work. And one of the big questions is, where should the data be that you're going to work on? There's so much of it, you don't want to give it to everybody everywhere. And so the Rubin Science Platform provides a web-based interface for querying the data still in the data centers in California, querying the images and the catalogs of data. The second feature is also assuming that a lot of work will be done in the California data centers. And that is a Jupyter notebook environment, which is for again, co-located data access and processing. And for that, they provide Python, that's a computer language, packages of software for use by the remote scientists. Also, those scientists can provide their own code for running on the California data center machines. The third way scientists can use the data is by using a web API, that is, application programming interface for remote access to the data. So in that case, they would make a query and get back data that satisfied the query and process it locally on their own systems. But of course, to access the Rubin data platform, you need Rubin data rights. And that brings us to citizen science, next to the last topic. The neat thing is that ordinary people like us can also participate in analyzing LSST data. The first way is by joining a Zooniverse project. The first LSST-based Zooniverse project is called Comet Catchers. But some established projects like Galaxy classification may begin to use Rubin data. There are several resources for the Rubin data community. One is discussion forums that you can join. Another is newsletters that you can subscribe to. And of course, as I mentioned, citizen scientists can also subscribe to LSST alerts through alert brokers. That would give access to those 10 million alerts per night. There are two ways in the US that you could do so. One is by going through Antares, which allows you to filter, flag, and classify alerts. It accommodates user-defined filters and also has a web portal. The other broker is Google, which facilitates analysis of the public data stream, provides filtering of alerts, and query services. And then finally, I have to admit that the data rights requirement does limit amateur involvement unless you can become associated with some institution that's doing astronomical research. Rubin, though, has a tremendous education and public outreach operation. It provides formal education with free online courses and classroom-ready materials. It's got an extensive website with images and videos and interactive applications. And then there's also support for the Zooniverse projects using LSST data that I mentioned earlier. So finally, the online tools. There are two of them that you might want to try. The first is Sky Viewer, which allows you to view the southern sky in great detail. It even allows you to see trails of asteroids that were detected on multiple images of the same area of the sky through different filters off. And so you get a multicolored trail for the asteroids after processing. And you can download Sky Viewer at skyviewer.app. So here is the cosmic treasure chest as seen in Sky Viewer. The cosmic treasure chest is an image 25 square degrees packed with 10 billion galaxies. And you can zoom in on areas of interest with Sky Viewer. For example, NGC 4261 is a large elliptical galaxy. It's not spiral like the Milky Way or Andromeda, but elliptical, probably the result of a big galaxy merger. And 4281 is a lenticular galaxy, which means it has a flat disk like the Milky Way, but no spiral arms. Another example is here, where you can see a pair of galaxies, NGC 4411b and 4411a. They appear to be related, part of a group, but they don't interact. So maybe they're only an optical pairing. And then contrast that with RSC G55, which consists of several galaxies that are pulling stars and gas and dust from each other. Skyviewer lets you turn on and off the tracks of asteroids that have been detected by the LSST. I counted 15 tracks in this image. Wait, it has, oh, hang on. Yeah, over here. There's one. Whoop. Coming around. But in case you couldn't see that, there's a better indicator. Okay, the other online tool is Orbit Viewer, which is even more fun. With Orbit Viewer, you can watch a simulation of the planets, asteroids, and comets in orbit about the sun. It's got the data to generate such simulation between 1900 and 2100. So if you want to see what the solar system was oriented like on your birthday, you can do that, or your wedding day, or any big day. You can zoom in, zoom out, and change perspective, zoom around the solar system, make it twist and turn. And you can download Orbit Viewer at orbitviewer.app. So I have a short demonstration of Orbit Viewer to finish up with. In the center, you can see the inner planets, Mercury, Venus, Earth, and Mars, as well as the near-Earth asteroids, Apollo and Bennu. In 2018, Bennu was visited by the spacecraft OSIRIS-REx, which brought back to Earth samples for analysis. The donut of dots there is the asteroid belt between the orbits of Mars and Jupiter. At the right in that belt is the minor planet Ceres. Jupiter is at the top. Saturn is at the lower right, partially hidden by the zoom out button. And at the left, you can see in red Eurybates, a Trojan asteroid in Jupiter's orbit. And above Eurybates, you can see the asteroid 2015 BZ509. It's interesting because it co-orbits with Jupiter, but in retrograde. So Jupiter goes around the sun in one direction. The asteroid goes around in the other direction, but they're in sync. So there's that. And at the upper right, you can see in sort of a green the trans-Neptunian object 2015 BP 519. And so let's watch the simulation. You can see how the speed of the simulation can be varied up to 1,000 hours of sky time per second of viewing time. By changing perspective, the user makes Uranus and Neptune appear, as well as Chiron, a comet with rings, whose orbit lies between Saturn and Uranus. In a while, Uranus is going to appear at the top. I'm not sure if we saw that or not. Yeah, there you go. It appeared and went away. And in about 40 seconds or so, Pluto is going to come into view on the left. So I'm going to let that happen, and then we'll conclude. But you can make all this happen yourself with Orbit Viewer. Change the speed, you can filter for what objects you see, what types of objects. You can ask which of these have been discovered by Rubin during this survey. So Pluto, there you go. There's Pluto. And so basically that's it. So I want to end the presentation with thanks to several entities: the NSF Department of Energy Vera C. Rubin Observatory, a Noir Lab from the NSF, SLAC from the DOE, because all of those provide useful reference material, images, and videos online. I want to thank Mary Duca, AAI Chair of Displays and Presentations, for allowing me to give another talk. AAI President Mark Stabinsky and AAI Vice President John Sickle for enabling me to use my own laptop in this presentation. Thanks to my wife Nancy for helping us test the use of my laptop last night. And finally, thanks to this attentive audience for your curiosity about our universe and the legacy survey of space and time. So that's it.
Any questions, Bill?
Yes.
The cryogenic minus 150 Fahrenheit for the cooling for the detectors, is that just to take away the heat of the processing, or does that have something to do with better resolution in the infrared?
That's a good question. I don't know the answer to that.
Okay.
We've got people in here who have much more experience with cooling CCD devices for imaging. I think part of it is thermal noise in the electronics that would be a particular problem with infrared. Okay, yeah.
Looking at the physical construction of the telescope, you have the center piece, and it seems to be held by these brackets or suspension arms. And they're doubled up, and it looks like wishbone suspension on a car. Does that whole structure move in and out on those support beams to focus? Or is that a fixed point, just like spokes on a wheel?
Yeah, you know, the only focusing that I've read about has to do with the camera, because when they change filters, it turns out they change the focal point of the device, and so that part has to be able to move to and fro. But you know, it's not like they're changing from one imager to another, where you'd have to completely refocus. Some of these scopes, like at Paranal, they can direct the light to one of three places, either a platform on either side of the scope or down below in the Coude focus. So in that case, if you change from one to another, you may have to change a focus. In fact, I know they do that at Paranal, because if they go from the Cassegrain focus to the Naismith focus, they have to change. And the focal ratio of the scope as a whole changes when they do that.
So
But here,
the actuators on the mirrors are not just compensating for the movement of the telescope, but actually helping.
I can't say that. I don't think they're involved in focusing, except by maintaining a uniform surface for the mirror or mirrors. Steve?
Yeah, they're using CCDs versus CMOS. Any reason?
I've never seen any explanation for that here.
The answer is history.
Mary Lou says it's history.
Just, okay.
Thank you, Mary Lou. Yeah, meaning what, Mary Lou?
So it was designed before CMOS were really, really good. And once the design is set, then you have to go with it.
Well, this scope has been in design for many years. Dr. Liu, who spoke last month in the auditorium, is a participant, as is Neil deGrasse Tyson, in developing the requirements for the scope. So that's we were fortunate that John Sickle back there got him for for our speaker to kick off the year. You may have seen him on Star Talk as well, so that's been a lot of fun. He spotted my shirt, by the way, this Vera Rubin mail order shirt that I got.
Could you just repeat, online tools again?
Yes, it's skyviewer.app and orbit viewer, all one word, .app.
Those you can get on cell phone.
Yeah, I think so.
I just got Skyviewer on my phone.
Oh, good. Okay, yes.
One last question. You showed the view, I mean, the amount of processing, the amount of everything that this device is gonna pull into our knowledge of the universe.
Yeah.
But it has a limited scope. It reminds me of like a belly gunner on a World War II bomber. It's got a limited
Right.
point of view.
Interesting analogy.
Has anybody figured out how many more of these we would need all over the northern and southern hemisphere to get a complete 360 degree? We need 5 or 6 of these. We need a dozen.
Well, it would be nice to have one in the northern hemisphere.
Yeah.
We don't have.
No. There are survey telescopes, but there's nothing of the magnitude of this operation anywhere else in the world. And I think my suspicion is that it's the hunt for near-Earth asteroids that drove it to success. Because if we don't detect one of those and it smacks us at the wrong time, we could be in deep trouble.
But that's only in the southern hemisphere.
Well, except
At the northern.
if you look at the North Ecliptic Spur that I showed you on the map, that's one of the purple areas. That's one of the reasons for going up into that area with the survey. Any other questions?
Make sure you ask the people online.
Online, any questions or remarks?
That was super duper. Thank you very much. That was great.
Well, thanks, Mary Lou. Coming from you.
Good presentation, Bill. Got a question. Have you run into any description of how deep the pixels are on those detectors? And I assume it's not an 8-bit detector like my cheap cameras, maybe, but is it deeper than 16 bits?
I don't know the answer to that. One piece of information is that I think it has a 16-bit output.
Oh,
Does that answer the question?
partially. I'm thinking that they have a kind of a standard exposure that they got to repeat every night. And that would sound like, if you have the exposure long enough to detect very faint objects, it's very likely that when you get a bright star in the field of view, it's saturated. And
Yeah.
that kind of limits the upper end of the brightness of things that you could do photometry on.
Yeah. The exposures are 30-second exposures, and they make 2 of those of each area of the sky when they're targeting that particular area. And I think they're separated by some time, but it's a very elaborate business designing one of these surveys. What do you take and when do you take it? And in fact, Charles Liu is one of the many authors of a paper on this subject. That's where I got the map of the regions. So, anyone else? So, you ready to go out and take on the universe?
I have a feeling that those subscriptions you're talking about are not something that one of us could get.
Okay. Well, that's a load off my mind.